having me. It's a pleasure to be here to speak in my now hometown. I know it's after lunch, so thanks for attending. I'm a core developer, and I love to do these presentations to expose what are core devs actually doing on Ethereum and how basically we make everything possible for you guys, the ones actually driving value to Ethereum possible. Today's topic, I'm going to face it for all levels. If you are a beginner, I'll try to get on board with you. And today we're going to speak about scaling. So just to get everyone on the same page, scaling refers to increasing the capacity of the chain to have more transactions. The way you do that is by achieving to lower their price so the chain becomes more democratic. Right now, Ethereum, as you know, it's a pretty expensive chain. Maybe not exactly now, but through its history. So only those types of activity that are highly valuable, like DeFi, are feasible to happen at the chain. If you manage to scale Ethereum to this meme dream of 10K TPS, then any type of activity would be possible, including social stuff, or other types of applications that don't have such a high transactional value. So why scalability has been also always a challenge is for this trilemma. I'm sure you have seen this chart. You cannot have the three of these. And Ethereum always prioritizes security and decentralization over scalability. So to visualize why this triangle is so complicated, let's run through the trade-off that the most decentralized networks as of today choose. So we have Bitcoin and Ethereum, who purposely limit the cost of running a node. That's to make, hopefully, as many solo stakers as possible run nodes at home. We limit how much bandwidth you're going to spend, how much RAM you have to have, how much disk you have to have. And that puts a limit on how many transactions the chain can process at a moment of time. If we want to scale, we can choose a strategy of a chain I'm not going to name, and just make the cost of running a node higher. That allows to increase the capacity of the chain, but at the cost that running nodes becomes more and more infeasible. If you extend that to the limit, only a small cartel of highly specialized individuals run nodes, and then if they want to do something nasty, like 51% attack, you basically have no recourse. The only thing you have left is go to Twitter, yell, and be like, hey, these people are trying to steal our money, we need to do something. So you have to halt and do a social recovery. Kind of like the DAO fork we did in Ethereum. So this is pretty expensive, and ideally we want to automate that step on Ethereum. And that's exactly what rollups do. Rollups give you the certainty that the rules of the chain are not violated. Optimistic rollups, they do that with these dispute resolution and economic games. And validated rollups do it by construction with crazy math. So rollups achieve scalability in computation, but they still rely on data. And I'm going to talk about what data is and why later. But the key concept is that for a rollup, if data, so transactions or a state diff, becomes unavailable, they are fucked. So optimistic rollups, you can steal everything because you can submit a transition that no one knows the step. So this dispute resolution game is infeasible. For validated rollups, you can advance the state of the rollup into a place that no one knows exactly where it is. So you cannot construct a valid transition into something else. So you can do a ransom attack. Like you would have funds in this ZK rollup, and the only way to get them out is for you to give me half. So it's not as bad, but still pretty terrible. So the key concept is Ethereum's job now becomes to guarantee data availability. And who has to do those checks? Unfortunately, everyone. And so why that's the case? Let's look at this other diagram, this probably is the most important one I want you to take away from this presentation. And this is to understand why data availability is such a difficult problem. So let's run through two cases. We have a system where we have proposers that publish data, and then we have slashers that raise an alarm if this data isn't available. So on case one, the proposer is the malicious one. It hides data. Then the slasher raises the alarm, and immediately after, the proposer releases the rest of the data. Then, in case two, it's the other way around. The proposer is honest, but the slasher falsely raises the alarm. Then you, as an observer, at T3, you have no way to attribute fault. And that's the problem. Data availability is not a uniquely attributable fault. We cannot run math on this concept, so we cannot have rules like we do with computation. Therefore, that's why everyone has to check data availability, because you cannot delegate these checks on anyone. So execution, we scale with rollups, and data availability, we cannot scale it in this immediate way of delegation. So what we do is to shard. So we split the responsibility of who has to check which section of the data. So the most basic thing is exactly what we do now, which is everyone downloads everything. If you run a node, you would just download all the blocks, and by default, by construction, you achieve these data availability checks. The problem is that it doesn't scale. That's the first image that we saw. So the second idea, the naive approach, would be let's just check some of the data. We'll randomly sample and check this byte of this block, this byte of this block, this byte of this block. That's not safe, because those terrible consequences of the rollups breaking happen only if one byte goes missing. So this approach is not safe. Instead, what we do, and that's basically the strategy of Ethereum, Celestia, and all these strategies, is to extend the data with what's called an erasure code extension, such that now you only need to have half of the data in order to recover all the data. Now, when you do your checks, you just have to convince yourself that at least 50% of the data is available, and then you can have certainty that everything is. So that's basically the genius idea that unlocks everything. And just to summarize, like the way it's structured, you can do really, really small checks, and due to the probabilities tending really down to 0, we can sample tiny amounts of data and have the certainty that everything is available. So the roadmap so far, this is these 0 years is maybe like 2023. We had this realization that we have to go into the rollup-centric roadmap, but rollups wanted something now. They need scalability now. So the plan of the last hard fork was to introduce this cryptography as soon as possible while we figure out the actual DAS, which is the network component. It's really tricky. I'm going to talk about it now. So rollups want something now, and that's why we gave them proto-dunk sharding, which came on the fork this March. And it just, the unlock was to introduce a separate market for data independent of gas. And what that has allowed is that because utilization of blob data is under the target, fees has been mostly 0 for now. And if you have used L2s, you have noticed that transactions now are practically free, and that's because of this. A funny side effect I want to talk about is if you have been following the ultrasound meme that ETH is deflationary now, because rollups are essentially not paying for anything, because fees are 0, now we have inflation again. And I personally think this is a good thing. Like, Ethereum is not here to make ETH holders rich, it's here to make a useful system that everyone can use. So, I don't know. My take is that this is perfectly fine, and we eventually want to go to a place of equilibrium. This is the roadmap, basically, in a technical sense. Now we have no sharding, so you can see that it's a one-on-one relation. Everything that the node custodies is everything that the network produces. What we want to achieve is a downwards trend where the actual load for the node, the data that you have to custody, is not a one-on-one on what the network requires. And even try to trend it down so that nodes have to custody less and less and less data. So PeerDAS is the first step that we are developing right now, and it has a modest sharding coefficient. The higher you go in the sharding coefficient, the harder things get. Because you have to, in a very timely manner, figure out who has what, retrieve it, and verify it, and do this thing called reconstruction. And this is a lot of concepts that are new to blockchain and new to Ethereum. So we are still trying to figure out how can we do that in a way that's resilient, safe, and not exploitable. Today, again, sharding, we have these blobs. That's the data that rollups would post. And what we do now with PeerDAS is extend them with the erasure encode that we talked before, and we chop them vertically in these units that we called columns. These columns are both the unit of custody and the unit of sampling. So in PeerDAS, the key of this protocol is that we are not introducing any crazy new networking structure. We are reusing components that we know and love and we have used for a long time. So let's run down how it's going to work. The proposer, as today, chooses a set of transactions, some of which would be blob transactions. These are the ones that include data from rollups. Then it does this extension, this math. Then it chops them into columns. And some of these columns are sent by GossipSub to the custodians that need to have them. And then the second step is the sampling. That's what actually gives us the sharding. The samplers would do checks, random checks, on some of these columns. And again, if 50% of these columns exist, or they see them and are valid, they consider that the whole thing is available. And that's the key to scaling. They only check some things and convince themselves that everything is available. But there is a problem. So the attesting deadline is a 4-second window today that attesters had to meet before they cast a vote and then decide if the block is available or not. And this deadline is pretty tight. What we have seen in testing, since we have developed this feature, is that some attesters miss the deadline. Doing this sampling is not an easy task. It involves retries, there is network issues that could arise, so some people get left behind. And unfortunately, those that left behind tend to be those that have not the best bandwidth or not the fastest computer, so the solo stakers. So this is kind of annoying because now we are introducing a centralization factor where we are incentivizing people to have good bandwidth and good connections in order to have not a penalty when doing sampling. So what Francesco, who's an amazing, brilliant researcher at DF, realizes that maybe we don't need to do sampling. And the realization for that is to distinguish these two concepts. So global safety is the key property that we all want to achieve, which is the block available? Are rollups safe? That's the most important we want to guarantee under all conditions. And the second one is individual safety. So, for example, can you be convinced that the block is available when in reality it's not? That's individual safety. So achieving individual safety is actually pretty hard, and that's what we would get with sampling. But it turns out that if we just have enough custodians custodying enough data, we can achieve global safety with no sampling. And that's the realization. We're going to move the attesting deadline from sampling into custody, so we only do the initial distribution on the first 4 seconds. And then sampling would be an optional task for anyone that needs additional safety. So if you're running like an exchange or some high-value application, then you can do sampling to get this extra level of safety on top of it. So the issue with this approach, actually, is the more data that we distribute on the first mechanism of custody is with GossipSub. And GossipSub is very efficient, it's very safe, but it's very expensive. It has a 4x penalty due to the way that the mesh distribution works. So eventually, we want to move as much load as possible from the first distribution to the second, so we can achieve this scaling factor that we need. Otherwise, in practice, the bandwidth that nodes perceive would not be much more or less than the status quo. So that's the current design, and it's technically not PeerDAS, that's just being very subtle, but this is what we call subnet DAS, because we are doing sampling, but instead of through peers, through these subnets of GossipSub. And I mean, it's great, because for me, as a client implementer, this is a massive simplification. I'm very happy with this design. So, PeerDAS progress. I updated this slide today, because unfortunately, as of a month ago, PeerDAS have been descheduled from the next fork, which is Spectra, into the next one, which is Fusaka. So hopefully by Q4 2025, we could see this. I think in the meanwhile, for Spectra, we will probably just increase the number of blobs in the network without actually introducing sampling to have a little bit more scalability in the meanwhile. Since then, We did the initial interop and proof of concept in Nyota, which was an amazing event held in Kenya. And then we have been doing devnets, each one dead and active later. Again, I think this has been proven to be much more challenging than we all expected. Devnets just keep failing for no reason until we figure out. So yeah, hopefully by Fusaka, 2025 Q4, we could see PeerDAS in mainnet. And even though we're still in devnets, this stuff is working. We have working prototypes. I think all clients are now catch up to the latest spec. And yeah, we're running devnets, so here are some fun metrics to look at. And that's until today. So PeerDAS is the first iteration, but we want to do so much more. When we want to go to these very high levels of sharding, like 4x, 64x, we need to do something even better. And that's what's called the 2D dank sharding. This is the final roadmap where we're going to go to. But doing this in practice, it's going to be quite complicated. To achieve it, we need to have some new networking constructions that we haven't found a design that's suitable yet. There is active research, and we have a couple ideas that are pretty solid on how to achieve it. But we're getting there. The key for you to take away from this is, if you remember from the original design, we had vertical columns. So a column is quite big in practice, but these red squares that you see here, they are tiny, tiny, tiny. I think about 500 bytes. So in the future with this, if you want to get a data availability assurance, you just choose maybe like 20 of these red squares, download them from the network, and then you can prove yourself that data is available. So this is so cheap and so tiny data that you could even do it from a smartwatch. And that's the vision of the future, that you could have a smartwatch which is doing these availability checks. It runs a snark verifier, and then boom, you have full nodes guarantee on a tiny device on your wrist. So that's all. Thank you so much.
So first, thanks for the talk. It's really clear. I'm more on the DeFi side of things. For me, it's like kind of the wizards in the towers are doing the thing to the magic to scale Ethereum. I'm at the application level, and it was really nice to understand better what's happening at the network level. My question was more about transaction finality and how it would be impacted by this. As far as I get it from your presentation, essentially, at least you'll need the PeerDAS sampling to occur to have some form of finality, so at least 6 minutes. Or can you expand on that?
Yeah, so finality is actually independent to this mechanism. Because what can affect finality is if due to the availability checks, the attester votes start to diverge and they are not useful, then that can affect. But when you vote for finality, you are doing FFG links, which are lagging from the head. So it's much more unlikely that they would be delayed or affected by the cost of sampling. This would be more of an issue of the tip of the head that would be unstable, and we could have more reorgs. But it shouldn't affect finality.
Oh, all right. And so how, in a major PeerDAS with all the implementation, what is finality looking like in terms of delays?
Yeah, so it's in PeerDAS, finality would be exactly the same. You would have
no change
attesters voting from a checkpoint to the other, and when you have justification and then finalization, then yeah, you have the same economic guarantee that you had before.
All right. Thanks.
Yeah, thank you.
Hello. You have an interesting concept, but I was wondering, since you're so young, how much did it take you to develop this concept?
So the concept of sharding has been on research for a long time, and this final design came from Dankrat. He's a brilliant researcher from the Ethereum Foundation, but I think many of these things come from iterative research. Like the Ethereum Foundation has been thinking about scaling since Genesis, since 2014. So it has been years and years and years of pondering and going in circles and seeing what can be done. Even at the beginning, the original roadmap was to do full sharding, not only of data, but also execution. So you have independent block producers, but that whole shenanigan it was attempted, but it turned out to be so complicated that yeah, people started to look, okay, what can we do? What can we simplify? And then the key realization was that if we give up sharding proposing, so we'll have one proposer that has to do everything, which in a way it's centralizing, but we can take that sacrifice. Then we can massively simplify the design and only shard data. And then for me personally, I didn't come up with any of this. Like all of us try to contribute where we can, but my role specifically is a client implementer. So we basically take this design and implement it in practice and try to find as many optimizations as possible to make it feasible.
Thank you.
Sure.
About data availability, and I understand that this approach, by having access to very small bits of the data, gives you assurance that the rest of the data will be there. So I understand that for this you're using erasure coding, and based on that, I was wondering what is the percentage of the data that have to be there so that the rest can be like reconstructed or like reproduced.
Sorry, I don't hear the audio super good. So you're asking what fraction of the data has to be there for reconstruction?
If you have, maybe if I close it, it's better, yeah. So I understand that with erasure coding, you just need to have a small amount, small percent. Can you hear me better now?
I'll try.
Thank you. Thank you. So with erasure coding, I understand that you only need to have available a small amount of data, small percentage. And I was wondering, what is this percentage? Should it be like 10%, 50%, 70%?
So in the current construction, it's 50%.
50%,
yes.
Okay. And how, based on, you will picking very small bits of the data anyway to make sure that you have access to the rest of the data. What happens? How can these very few small bits give you assurance for the rest of the data? Because it's just like 50% the one you have. So again, you are playing with the chances, if I understand correctly, that you will get the correct parts.
Okay, so you're asking basically how reconstruction works.
I just want to, if I understand correctly, you are only playing with the chances that you need to hit the correct parts of the file to make sure that the rest of the file will be available. Yeah,
so in the 2D wall, for example, if you have exactly 50%, you can do reconstruction, but it's going to be really complicated because you have to solve a Sudoku. So I would say the closer you are to exactly 50%, the more difficult would be. Like, even though it's mathematically possible, it can be pretty complicated. And we always work in the assumption that there are some actors in the network that have everything or have a large part of all the data. Like in PeerDAS, we have a concept that's called supernodes, where they have absolutely everything. So for them, doing reconstruction is trivial because they always have everything. For 2D, the goal is to implement distributed reconstruction. So it's going to be this complicated procedure where someone has a column and then reconstructs this other column, and then these people do the row, and you have like this Sudoku and eventually recover it. But yeah, like mathematically, if you have half the data, you technically can do it. What's then specified is how many rounds of iteration you need to achieve that.
Exactly. Okay, cool. Thank you very much. Thanks a lot.